Ben's a formal FNL member. He runs, helped run the club for the group for a while, and he's coming back to present here. So this is something you guys can also do when you do go out in the wild, wild west out there. Get jobs and other things, or maybe run companies. Come back and present or talk about your successes. So with that stated, Ben, is that better?
All right, so this is a speech. Today I'm going to be talking about analyzing audio using machine learning, and specifically we're talking about audio of bird calls. Next slide out. So traditionally there are two different ways to monitor wildlife populations, and the reason you want to do this is to monitor whether the populations of endangered species are increasing or decreasing, whether there's a new invasive species in the area, and generally it's just good to know ecosystem health. So one technique that's commonly used is camera traps. That's where a researcher goes out and clears some bush, sets up a camera, and then just lets it record. And these can be either manually labeled, where someone has to watch through the whole video and label what animal was where, or they can be automatically labeled using machine. The problem with this, though, is that it only really detects larger animals, so we're missing out on birds, insects, and rodents. The other technique is using an audio array, and from now on I'll call this putting a microphone in a bush, because that's really what it is. This does a good job of recording noisy animals, such as birds, and it also does not pile up a bunch of data. So you can set this running for a month and hopefully don't run out of battery and don't need that much storage space. But it is much harder to extrapolate results from audio data compared to. So how can we turn audio into a form that's easy to analyze? So Alex, can you hit the audio button? Basically, audio is recorded as a waveform, and that just tracks what the air pressure is at each point in time. And just looking at this graph, it's hard to tell what it would sound like. All you can see is how loud it is at each point in time. What we do is convert it to a spectrogram, which is a representation of what frequencies are at each point in time. So on the y-axis, we have different frequencies, and on the x-axis, we have what time it is of the recording clip. So this is 12 seconds long, same as this waveform. The frequency, so each pixel in this image, the brightness is how much of that frequency is represented at each point in time. So right here, where it's kind of yellow, that means that frequency 5000 is very strong at around 4 seconds. So next slide, Alex. And that makes it much easier to recognize patterns because we have a form that is a better way to visualize the data. So now we need to figure out how can we turn this spectrogram into a species label. And machine learning, they just say, oh, it's a mysterious black box. We have some input and some output, and it's like some mathematical function. Today, I'd like to not just call it a black box, but look at what is the structure of this black box. You never fully understand how it actually works, like what numbers are actually being applied to this spectrogram, but you can at least see like what process it kind of goes through in order to narrow down a gigantic picture into just one result. Okay, so we're processing images, and a common technique in image processing is a convolution. There's a good 3 blue, 1 brown video on this that I would recommend watching. I'll try to kind of explain what's going on. Basically, we have an input image and an output image. And I like to think of a convolution as some kind of filter. So this filter, we're going to overlay it on many different regions in the input image. So right here, we have this 3x3 region, and we overlay it around this blue box. Each number that's overlapping, we're going to multiply, and then add up every number in that result. So here, 1 corresponds with that 10. This 1 corresponds with that 10. So 1 times 10. This 10 is overlaid with this 1. 0 and 10, 0 and 10, 0 and 10. -1 and 10, -1 and 10, -1 and 10. So on the left side, we have 10 times 1, 10 times 1, 10 times 1. That adds up to 30. In the middle, we have 0. And on the right side, we have negative 30. So the total sum of that is 0. And that's why we have a 0 in the output image. The same goes for this magenta box. We overlay it and we get a result of 0. However, when I put the convolution on the green box, we end up with 10 times 1, 10 times 1, 10 times 1. But on the right side, we have 0 times negative 1, 0 times negative 1, 0 times negative 1. So the total sum there is 30. And that's why there's a 30 in the output image. And the reason this is a filter is that it extracts what kind of features are in the input image. So if you think about what this would actually look like, it would look like a white panel of high intensity and a black panel with no intensity. The output image here is 2 black panels and a white line in the middle. And what that white line means is there's some kind of edge here. So this convolution is a vertical edge detection. So we're not just going to apply one convolution to our input image. We're going to apply many different convolutions. So these are 8 different edge detection kernels, and then this one's a blurring kernel. So you can see it's detecting different directions of edges. And if I was to take the absolute value and add them all up, I would get some kind of outline of what these fly. So we're not just applying one convolution, we're applying many. And the goal is that through these many different operations we're applying, we can hopefully extract something meaningful. Okay, now this slide is really dense, but I will go through it slowly. It might take like 5 minutes. So the goal here is taking an input image of a handwritten digit and get some output for what digit it thinks that is. Here is a 2, and this here is a mathematical model. The terminology I'm going to use is that each operation we're applying is a different layer. So we have an input and an output, so that's a layer. An input and then an output, that's another layer. Input, output, layer, input, output, and you have 7 layers. The first layer is applying the convolution to the image. You can see that the input has 1 channel and the output has 16 channels. So how did that happen? We had to have 16 different kernels, so we're basically applying 16 different filters and getting the results from that. So this might be extracting like vertical edge detection features, horizontal edge detection features. It could be detecting if there's a right point surrounded by darkness, stuff like that. Then we have to reduce this gigantic number of numbers so we can slowly get it towards just 10 numbers. And the way there's a lot of techniques to do this, but the most common one is max pooling. So you just take each 2 by 2 region in an input image, you find the max value in that region, and then that's just 1 value in the output image. So you effectively reduce the image size by 4. We apply another convolutional layer, except this one is more complicated because now we have 16 input channels and 24 output channels. So how did that happen? This is because the convolutional kernels that correspond on the input layer actually have a different kernel for each of the 16 channels. And we're going to add up the results from each of the kernels applied to each channel, and that's just going to be 1 pixel in the output image on 1 channel. So each kernel that's applied on the input is 555 by 16, so that's 400. And then we have 24 different kernels applied, so that's 9,600 parameters. And you can see that it's quickly going to grow in the number of parameters we have to add. Then we apply max pooling again, so we reduce the number of numbers we're using. And then at this point, we're switching from a convolutional neural network design, we're switching completely over to a fully connected neural network design. So now that we've reduced the number of numbers, we can flatten it, and that just means scan across each image and just not like order them. So 0, 1, 2, 3, 4, 5, 6, 7, and then you have some gigantic list of numbers. This list of numbers is then going to have a connection to every number in the next input and the next output layer. So it has like some connection strength. And the way we calculate the next output is multiply the input node by the connection strength, and then just add that all up for each of the different input nodes. So basically, every single feature we've detected in this flat layer can somehow affect every single node in this hidden layer. Finally, we need to scale that down to 10 different numbers. And the reason we have 10 outputs is it's much easier to tell the model which direction it needs to go in to get to the right answer. So say it took this 2 and it misclassified it as a 5. Instead of saying you need to go from 5 to 2, passing through 4 and 3, we're going to say you need to decrease the 5-iness of this and increase the 2-iness. So it doesn't have to think that 4 is closer to 5 in some visual sense because it's not. Next, we have to figure out how can we change these parameters so that we get a model that's actually accurate. Initially, every single parameter starts out as some random number. And so for any input, you get a random output, of course. But the model we were working with had 25 million parameters. So that's not something you can change by hand in any capacity. So go back to the slide. So we need to figure out how can we automatically change these parameters to get the model to be right. Well, what we do is take some expected output. So here, every number is a 0, except we gave it a 2-iness of 1. And then we compare that to the actual output. And basically it's some kind of distance calculation, but it has logs. I don't actually know what it is. We take some distance between the output and the expected output, and that's our loss. And loss just means how poorly did the model do. The goal of training this model is to reduce the loss as much as we can. So if you've taken calculus, you'll know terms like the derivative, the chain rule, the product rule. And if you haven't, just think we're doing some math to figure out if we change some parameter in this middle process, how is it going to change the loss at the output? And
you judge the loss by the, okay, I'm saying that's a 2. Is it giving me a 2? So like a person has to do it?
yes, so each training example needs to have an actual label, and we need to actually know what it is. So we can't just give it input images and then it gives you some output, and you're like, well, I don't know what the right answer is. You can't train on that.
But it's done by a person, right?
Yeah, it's done by a person. So I'll get to that later. So basically, we're going to try and tune each parameter in this middle process to try and reduce the loss in the output. And one way you can do this is just go one image at a time and try and reduce the loss that way. But that doesn't work because the parameters will be hopping back and forth in some kind of random fashion. What we have to do is take a batch. So put in like 32 different input images, get out 32 different losses, and figure out how we can reduce the sum of that loss.
So the idea is to just unblur it as much as possible? Yeah. So like we have like an input and we're trying to change it and get it to like what the expected output is to be.
Yeah, we're trying to get a really crisp expected output that's like, this is for sure a 2, and I'm certain that it's not any other number. That's what we want. And that's the goal of reducing the loss to 0. So skip 2 slides, Alex. So now that we know how we're changing the parameters, how do we actually get these training examples? All of our training examples come from a website called Xenocanto, and that's just a place where someone can take their hobbyist bird recordings and upload them to the internet with some label on it. And our model, we designed to take in 5 seconds at a time. So we need to figure out how can we split up a 1-minute audio clip that they uploaded and feed it into the model. So traditionally, people have done a technique where they just take 5 seconds at a time in consecutive order and feed them all into the model. But say you got a chunk right here, you're just giving the model background noise, and it's not exactly learning on the actual call, which is right here and right here. So my team in the past developed a technique called PyHaw, and that just uses someone else's model to detect where in the clip is there some kind of bird noise. And it doesn't know exactly what bird noise it is. That's what we're trying to work on. It just knows there's some kind of bird noise here. And we use the label on the file level to just attach that. So if someone said there's a screaming peehaw in this clip, we just assume there's a screaming peehaw here and there's a screaming peehaw here. And then we put that all in PyTorch to train a multi-species classifier. And this is another slide on the chunking methods. We call the traditional chunking method raw chunking, because you're just taking it in and doing raw chunks on it. And then with PyHaw, you find these annotations where it believes there's some kind of bird and put the chunks on that. Next slide, Alex. And as you can see, PyHaw is performing much better than our simple raw chunking. So on the y-axis here, we have some kind of accuracy metric, except it's a little more complicated because you might have multiple birds at the same time, so you can't say this is right or wrong. And then on the x-axis, we have the number, the progress through the training process. So it does 10 epochs, which just means go through the entire training data set 10 times. And this might take like between 3 hours and 24 hours, depending on what other parameters we have set up. But as you can see, PyHaw is training much faster than simple raw chunking. However, that doesn't mean it's performing as well on the use case we actually designed to use it on. So here's a graph of training accuracy as we train the model. And you can see it's leveling off at about 0.6. But here, our testing accuracy is leveling off at about 0.2. And our testing data set is someone put a microphone in a bush in Peru for 21 hours and then manually listened through all of it and labeled every single bird they heard with some species label. And that's a lot of effort for a bird expert, so I wanted to mention that. So it's not performing as well on the microphone in a bush technique that we wanted to. The reason for that is a common problem in machine learning called domain shift. Basically, our training examples are very different from our testing examples. So the training examples, someone went out and recorded a bird, just specifically one bird, and uploaded that to the internet. Our testing examples, they put a microphone in a bush, and it's hearing many different birds at the same time, but a lot of background noise. There's insects, which you can see are these constant bands right there that just kind of mess up the picture. And the birds are farther away from the microphone. And one of the key parts of this is higher species density. That just means that there's more birds calling at the same time from different species. And one of the metrics we had was for every 5-second chunk in the testing data set, there were on average two different species calling at the same time. So the expected output in that had 2 different bird species, and it's only one input image. But that doesn't mean we're performing as poorly as other people have done in the past. This is a graph from a machine learning competition in 2020 using this exact same testing data set. And we were working with the Peru data set, so that's in purple. The best model got a accuracy metric of 0.07. So considering we were getting 0.2, I think that's rather impressive, but we weren't able to create anything that was really publishable by the end of the summer. Yeah, there's a lot of research frustration that you don't get the right number, but I guess that's the whole point of research. We had a Google sheet that just had like we were comparing PyHaw versus raw chunking, and we had a Google sheet that was like the accuracy metric on the testing data set, and it was like not that different. We expected to see a difference. So research is frustrating, I guess. So some common features of an REU. So I did an REU over the summer at UC San Diego. I don't think I mentioned that. But an REU is a research experience for undergraduates. So probably the best part is you get paid for work experience. They gave me a stipend of $6,000 for 10 weeks. And then they paid for housing, which was around $3,000. There was a food allowance, $1,500, and then they reimbursed travel. So you get compensated pretty well considering you're an undergraduate. You also get to work with a lot of peers and make connections. So there were around 20 people in my program doing 6 different projects. And since we were from all different parts of the country, really we spent most of our time hanging out with each other. Sadly, on the making connections point, our research advisor was kind of distant. So hopefully if you do an REU, your situation will be different. It also shows you what grad school looks like. So one of my coworkers was a master's student, and I got to see what is he working towards to finish grad school. Cons is it's usually really highly competitive. So the program I applied to had 300 applicants and could only accept 10 people. And I applied to 6 different programs, and that was the only one that interviewed me. So I think I got kind of lucky to get in there. Usually they have a minimum requirement of like 3.0 GPA, but outside of that, they don't really focus on classes that much. In my interview, mostly they talked about project experience and what technologies or skills you had. So I talked about FNL a lot, basically the whole time. I mentioned that I had C++ experience, a little bit of TypeScript, and a little bit of Python. And I ended up working completely in Python for the whole summer, so it's not really important that you know exactly the technology they're going to use, but that you know something in that kind of field. So for example, one of the projects required someone to design a PCB, and they hadn't used that specific piece of software yet, but they had designed PCBs on different kinds of software. So that was the interview process. And now I'm going to go over to the website to show you how you can apply for these. So the website's etap.nsf.gov, and I have to log in every time because they're nerds. Okay, it's for my security, supposedly.
That doesn't look like you, does it?
That is not me. You were right. That's not me.
I got some image processing skills too.
Okay, I'm gonna go to search opportunities. So right now there aren't a lot that are open because usually the applications are due between December and February. But I guess program coordinators, they take their time, so you'll have to wait. But some are open right now. So for example, a lot more open since I last checked. Here, this one, summer research at the interface between chemistry and biology. So they have these in all different kinds of fields: chemistry, biology, physics, math, computer science, astronomy. I missed one, sorry. So usually on these, they'll have an overview of what the program is about, what the research focus is, eligibility requirements. So that one, the minimum GPA was a little higher. You'll have to look around. And it is not open for applications, but I'll look at this one. Sure, and the requirements. That one does not have as much as it normally asks for. Normally it asks for resume, a couple letters of recommendation, and personal essay questions. So etap.nsf.gov is the website you should go to. I'll post the slides later so you can find that if you want to. And then right now I'd like to open the floor to any questions about the entire presentation. Yes, Juan.
Why didn't you guys use more landscape samples rather than just use the samples?
So why we didn't train on that many soundscapes?
Yes.
So the problem with that is we did not have nearly enough data to actually train on soundscapes. That 21 hours I mentioned was all we had. So if we were going to train on that, we wouldn't be able to test on it. So you're losing that if you're training on it. And really 21 hours was not a lot of time considering how much data we were training.
Could you guys do some sort of like put in different microphones that only need equipment to like pick out different bird sounds? Like kind of like sorting before you go through the machine.
Yeah, so there's a lot of different pre-processing steps you can do. You can change how the spectrogram looks, so you can like scale it up so that you're looking at more frequencies, but then you kind of lose some fidelity on the time axis. So yeah, what you're saying, you could cut off higher frequencies, but the range of frequencies of different birds is pretty vast, so I don't know if that would be particularly helpful. But there's a lot of different pre-processing techniques we could use. So one of them was to put the power of the spectrogram through the log function, and that kind of made the more powerful signals stick out compared to the background noise. So yeah, there's a lot of different things you can pre-process.
So you were taking the transpose of the matrix and multiplying by the kernel, and it's taking the 9 squares and like basically condensing all the input down to 1 square.
Yes.
And it was still able to distinguish, like if there was 2 birds playing, it thought there was 2 birds later on, like it didn't blur the data and think it was just 1 bird of a different kind.
Well,
That's kind of neat.
it wasn't particularly good at that.
Okay.
I'll admit that. But there are different kinds of features it's looking for. So it can you can kind of have like one bird, like the features from that, and then it's kind of adding the features from another bird, and hopefully in that final layer, it can recognize that this feature vector is like representing 2 different birds.
Huh.
But that's a really tricky thing. And honestly, it didn't perform that well on recognizing multiple birds. A lot of the time in soundscapes, it was confidently wrong. So it would say, there's this specific bird, I'm 99% confident, and then you look at the labels that the humans gave it, and it was not even there. So hence why we were getting like 20% accuracy.
To be fair, though, I mean, your training accuracy was like 60%. So
that was only for 2 epochs. Only our validation accuracy was getting up to like 80%.
okay, because you can usually see like maybe 60%.
Yeah, so we were getting like training like 0.9 and then validation of like 0.8. But that graph was like kind of cut short because the testing accuracy leveled off, and it was silly to have it just flat.
So you did a machine learning project, you created a predictive model. What was the hardest part of the whole process?
Looking at the numbers and not knowing what to do to make it better. I can show you guys the spreadsheet of what the numbers were, and I was like, well, this took us 10 weeks, and I don't know what to do at this point. So for the first bit, I was just looking over the code base. They had like a really sloppy implementation from like a couple months ago. So some of the files had like indentation errors, and it was all in Python, so that's like a really big problem. And so that was like the first couple weeks. And then after that, I was learning techniques like using SSH. I set up cloud compute servers on Amazon Web Services so we could upload our data, start it running on some machine in the cloud, and it would finish much quicker than if we were running on a local machine. And then for the last little bit of it, I was setting up a bunch of different testing scenarios. So we were testing 6 different chunking techniques on 4 different data sets. So that meant we had to do 24 different model run-throughs. And so I had to like move the files to the right server, make sure it's set up, make sure I tell someone to not also train on the same server because that will crash the other training sessions. That took about a week. And then A lot of the rest of it was just coming up with ideas to our which it didn't go that far, but they're going to continue this throughout the school year at UC San Diego on a volunteer basis. It's not going to be like full-time every day. Yeah, no money. That's why I'm like, okay, I'm good.
How many decisions did you get to like make on your own, like decide which direction the project went?
How do I answer that?
Well, I know they give you guidance, they tell you what the project's about, they give you the stuff and tell you what's going on, but like, as for your REU experience, were you able to like work in the direction you wanted to go to see if something worked? You said you had a bunch of different parameters you were choosing. Did they pick all the parameters for you? Did you come up with different things on your own?
We kind of fumbled around with the parameters, but we made sure for each test that all the parameters were the same, of course. I had a little bit of direction. So for 2 weeks, I was working on a technique called pseudo-labeling, where you take an unlabeled soundscape and just run it through the model and try and build up confidence. So if it's really confident, you say, you start training on that. So if it says, I'm 99% confident this bird is here, you're gonna say, okay, we wanna reinforce that with a training example. So that was something I worked on for about 2 weeks, and I kind of decided to do that on my own as I think, let's investigate how this works, because we had to do a lot of literature review, like reading papers of what other people had done in the field, and that was like one technique that stood out to me. So I got to decide on like the direction I went for that.
It's pretty cool.
Can I comment on that in general? So the National Science Foundation funds usually between 3,000 and 5,000 REU projects a year in any discipline you can think of. So you don't have to do engineering for these things. That's just what this group. Was your lab an engineering lab or was it a biology lab?
It was mostly focused on solving problems using technology to help the environment.
So how much decision you get, how much ownership you have in your project, it depends on the lab. So like his lab, it sounds like you were part of a project, but you weren't the leader. It wasn't your project that other people helped you on. So I used to have, when I was in grad school, I had 2 RU students every summer that I would work with. And for the way we decided to do it was I would take a project that I had on my list that I wasn't getting to, and I would give it to one of these students, or pick sometimes the pair, and they would actually do the whole thing and say, I'm available, you can meet with me, I'll mentor you, I'll help guide you, but you get to make all the decisions. So anything in between, it really depends on the lab. So that's an important question to ask while you're interviewing, is to find out what's expected of you, and so that you can get in there and meet those expectations, so that you don't come in thinking I'm going to take over when you're one of 5 people working on a project, but also that you're not like, okay, let's get started. Here's your project, have a good summer, we'll see you in August.
Yeah, so I'll give a little more context on that. When I was accepted into the program, I wasn't assigned to a project, and they didn't do it until like the 3rd day of the program. So we spent the first 2 days like touring the campus, just like making sure we're like talking to each other and like learning about the projects, and then we kind of put a vote in for what project we wanted to work on. So I noticed, acoustic species identification, like I think I can help with that. It's completely in software, so I don't have to do anything mechanical engineering. And I like talked with the project lead and kind of like shoved my way in there, so they would assign me to that. But yeah, there were different projects like in the same program. There was a mechanical engineers there. There were people working on a surfboard fin that could detect different like salinity sensors in the ocean, so they could have more refined data on like ocean temperature, stuff like that. But yeah, it's not just like engineering and we're gonna assign you to this project. It's like you're gonna figure out what you're doing in as many different disciplines.
Something else with Josh's comment, not all REUs go through the NSF also. So like if you're looking for REUs, you don't see something on the NSF website, just do REU, type in your major, and look at the first 30 websites that pop up.
REUs get funded through individual research grants too. That's how we did ours. Is my PI, my professor advisor, would ask for extra money, and that would bump her priority up for getting that grant by saying, yeah, we'll take REU students all summer long, and then you get a better chance of getting your grant. So there is multiple ways in. So networking is really useful, and kind of working into conversations that you might be looking for an REU when you meet a research professor.
So when I first heard about this, Quinn, it was because Quinn told me, you should apply for this robotics REU in Oregon. And I was like, okay. And he wrote me a letter of recommendation, Joe wrote me a letter of recommendation. And I applied for that. And then about a month later, I realized, wait, there are a bunch of different REUs in many different places. I should also apply to a lot of this. So apply to more than one, of course. Hopefully you get accepted.
Also, not all places host REUs, but they may pay for their own research experiences as well. So if there's like a school that you have in mind, you can always Google them and look at their departments, and they may have actual positions there where they'll still fly you out. They just don't post it on any of the websites. Like Johns Hopkins flies out like 2,000 people a year to do research there, but they won't advertise it outside of their website. So
That's dedicated right there. That's really dedicated right there.
Go to each school's website.
Right.
Look for every instance of the word research.
Sounds like a programming problem. Web scrape everything.
Right.
I think Google already does it.
Okay, any other questions? So I'll wrap this up. You guys can start working on your projects or socializing. The sticker printer is out right now. There's like barely a little bit of food left. So have fun.
And a huge shout out for Mr. Redden for not hijacking that conversation.